Hello, in this video I'm going to continue our journey through the different types of astronomical objects. Now in the last video we looked at the moon. This video I'm going to move that little bit further away from the Earth and look at the planets. So obviously we're still inside the solar system. And in the solar system, if you ignore the sun, which has got about 99.9% of all of the mass, then the vast majority of everything else that's left is in these 8 planets. I mean, Jupiter and Saturn on their own account for 90% of what's left outside of the sun. And then we've got the other 6 to add in. So this is where it's all happening. And this picture here of the 8 planets, now it's to scale in one sense, but not in another. So they've put the sizes of the planets to scale, but they haven't put the distance from the sun and the separation of all the planets to scale. So let's start with the sizes then, seeing as that's fine in this picture. And you can see we've got 2 groups really that we can split up into here. On the left, we've got these 4 small planets. This is Mercury, Venus, Earth, and Mars. These are the terrestrial planets, rocky planets, things that have got a definite solid surface. So we've got those 4, and these are the ones close to the sun. Then there's a bit of a gap, which I'll get onto in a minute. And then we've got the 4 big planets, the gas giants on the outside. Although the outer 2 are sometimes referred to as ice giants. And these 4 are non-terrestrial planets, as in that they don't have a definite surface. So even when people talk about ice giants for Uranus and Neptune on the outside there, because we've got Jupiter, Saturn, Uranus, Neptune. So with the outer 2, when they're called ice giants, that's not to say they're like big spherical ice cubes where you've got a solid surface. They still don't have a definite surface. They're just a bit icier than Jupiter and Saturn, which are very much gassy. So although there's liquid on both, you've got liquid, you've got ice, you've got gas. The point being they're not solid. So that's what you want to keep in mind with those. There's no definite surface. Now in terms of distance from the sun, now we know that we refer to the distance of the Earth to the sun as 1 astronomical unit, just because it's easier to refer to that as a unit of distance in the solar system than saying, oh, well, the Earth is about 150 million kilometers from the sun or 96 million miles from the sun. And plus, of course, none of these numbers are exact anyway, because as we know from Kepler's first law, the orbits are not perfectly circular. They're slightly elliptical. So the sun isn't at the center of a circle that the planets are orbiting around. They're ellipses that they're moving in, so oval-shaped courses around the sun, these orbits. And some are more elliptical than others, which I'll mention as I go through them. But if we go off of this 1 astronomical unit for the Earth, so here's the surface of the sun. I'm going to put the Earth close for a reason that I'll get onto in a minute. So say that was 1 to get out to the Earth. That's got us to our 3rd planet out. Well, ballpark figures on these, Mercury is a little bit less than half an astronomical unit. So Mercury would be, say, about here. So say that was Mercury at about half. Then you've got Venus is about 3/4 of an astronomical unit. So say Venus was around about there. So that's at 3/4 for Venus. Then let's write these on over here actually. So Mercury, you're looking just a little bit less than a half, say 0.4, but let's go for half just to make it easier to remember. Let's get something that's going to stick in our minds. Venus is about 3/4. Then of course you've got Earth at 1. Then we're going to be going to Mars, and Mars is around about 1.5. So we're just getting that little bit further, bit of a bigger gap there to get to Mars. Right, and now we get a bigger gap because we got the asteroid belt between Mars and Jupiter. I'm doing a separate video on that. It's thought that there may well have been a planet that was going to form there, but Jupiter's so big it just disrupted everything. Now we're jumping out to about 5 astronomical units. So if that was 1 that we had here to get to Earth, then you're looking at 2, 3, 4, 5, and this is just roughly speaking. So we got a big gap there to get out to Jupiter at around about 5 AU. And you can see we've already covered the innermost 4 in that amount of distance, and we got a bigger jump than that to get out to the next one. So that's a big jump already. To get to Saturn, well, you're going another 5 astronomical units out to 10. So everything that we've done out to Jupiter, we've then got to do again just to get us to Saturn. So Saturn might be around about there, say. So let's ignore, yeah, these lines were just marker lines that I was putting in. So, and that's the sun that we've got there. So we got 1, 2, 3, 4, 5, and then 6. Then to get out to Uranus, and if you forget what order they're in, it's quite handy that the last 3, if you take the first letters, to spell out sun. So that makes it a bit easier. Uranus is then at 20. So we've got to double again what we've done to Saturn. So I'm already going off the screen here. And then Neptune, we're doing another 10 out to there. So that is a long, long way in order to get to Uranus and Neptune. So, you know, you can see on this scale that if we're saying, right, well, that's to get to the 4th planet, that's the 5th one, that's the 6th one, you know, starting from here, that's 4, 5, 6. And then 7 isn't even on the screen. And then 8 is, well, who knows where 8's going to be. I mean, it's so far off to the side. It's just nuts. So you want to keep that scale in mind. Right, now I'm going to just rattle through the 8 planets in turn, just trying to hit the high spots about what might be interesting in them. So let's start with Mercury then, the smallest planet. It is bigger than our moon, but not by a lot. You know, the moon is about 1/4 of the diameter of the Earth. This is about 1/3 for Mercury, but it's a very dense planet. So although Mercury is smaller than Ganymede and Titan, you know, the largest moons of Jupiter and Saturn, it's smaller than those, but it's got more mass. It's very dense. It's out of all the planets, it's the 2nd most dense after the Earth. So it has relatively strong force of gravity on it. You know, it's got a similar gravity, force due to gravity, as Mars, even though Mars is that bit bigger. You're looking at gravity being around about 1/3 of what we experience on Earth. I mean, looking at it, it has some resemblance to the maybe the far side of the moon, where you don't get the lunar maria. You know, it's heavily cratered, it's rocky. You know, it can look like some of the dwarf planets as well. It has that sort of feel to it. You know, it's not large enough or massive enough to really have any significant atmosphere. It doesn't have much of a magnetic field. It's got a bit of a magnetic field. You know, it can keep the solar wind at bay. But yeah, it's a fairly bleak, barren place. You know, for similar reasons to the moon, the craters don't get eroded. You know, there's no plate tectonics, there isn't volcanic activity, there's no atmosphere, there's no running water. So yeah, it does have that sort of moon sort of look to it. Speaking of the moon as well, you know, after we were talking about that, if you watch the video talking about tidal locking, there's a similar sort of tidal locking that goes on with Mercury. It doesn't have the same extent where it always has the same face pointing towards the sun, but it has very long days. You know, it orbits the sun every sort of 88 Earth days, and but you'll get close to a whole year, close to a whole orbit of having the same face just pointed towards the sun. I mean, they have very long days, you know, where you'll just get one side illuminated for you know 88 days or thereabouts, you know, even more. So yeah, it has its own form of tidal locking, and it has quite an eccentric orbit for a planet. So you end up getting, you know, the combination of the two, of having a fairly eccentric orbit plus this long periods in sunlight and long periods in darkness. Get a very large temperature range, you know, from minus 170 degrees C if you're on the dark side to 420 degrees C if you're in sunlight, because you're so close to the sun. So yeah, it's has quite a range in temperatures, and the proximity to the sun makes it difficult to observe, really. You know, it's looking at it from Earth, you need to look at it near to just before sunrise or just after sunset, because it's always going to be fairly close to the sun in the sky. I mean, you can get sometimes the better views you can get to it is when you get a transit happening. We had one recently. Was it 2015? I lose track now. I remember observing it because we had a nice clear sky for it, fortunately. And that's where Mercury passes in front of the sun, and you just see this tiny little dot just moving across the face of the sun during the day. So that was quite a nice one to observe. I remember it was clear at the start for about the first half hour or something, and then it clouded over, and then I managed to see it again at the end. So that's probably the best view of Mercury I've ever had, really. I mean, it's so close to the sun that the Hubble Space Telescope is not allowed to even point towards it, just in case it ends up, getting fried by the amount of light that might come in. There's a possibility as well with the way that it's not tilted very much on its axis. Mercury, it doesn't have much axial tilt at all, so there'll be some craters at the poles that don't get sunlight on them at all. So similarly on the moon, there might be water ice there. You never know. It's going to be cold there if it's not in direct light, and there might be some water ice kicking around. So that's Mercury anyway. That's the first one. Let's move to the next one out, which is Venus. Fairly bland looking picture here on Venus. Is not a great one to look at, really. I mean, it is very bright in the sky. It's the brightest planet in the sky, but it doesn't have much in the way of features. It's shrouded in cloud. It's got a very hot, thick atmosphere. Mainly it's carbon dioxide and with a bit of sulfuric acid thrown in, so it is a inhospitable place. It's a similar size and mass to the Earth. There's not that much difference, and it's not that much closer to the sun, but this is greenhouse effect on steroids, really. And on Venus you've got all of this CO2, and it's just trapping all of the energy that's coming in. And you've got 450 degrees average temperature on here. It's just thick. It's high pressure, getting on for 100 times the pressure at sea level on the Earth. So yeah, high pressure, thick atmosphere, really, really hot. It's got a very slow rotation, probably because of this atmosphere. The thick atmosphere is dragging on it, so it takes a long time to rotate. It can orbit the sun in less than 2 Venus days. The amount of time. So it does one complete orbit of the sun, and it hasn't even rotated twice on its axis. So it's a long day on Venus just because of how slowly it's moving. Looking at it from Earth, I mean, this is what's the morning or the evening star, commonly referred to. Again, you're going to be seeing it relatively near to the sun. It's the third brightest object in the sky after sun and the moon. And you looking at it through a telescope, the most interesting thing is you will see phases. So sometimes you'll just see a crescent Venus. Sometimes you'll see quarter Venus, half Venus, whatever it may be. So you do get to see those phases. If you could see under the clouds, as some satellites have looked under there, and things have gone down and looked on the surface, it's mainly volcanic plains. You've got ridges, you've got craters, highlands, things like that. There's no plate tectonics. It's got a surprisingly weak magnetic field, considering that it's so similar in size to the Earth. But it doesn't have this internal dynamo, maybe because it doesn't have the plate tectonics and it's trapping heat in there. If you're going to get the dynamo that creates the Earth's magnetic field, similar thing on Venus, you need these convective processes going on from the core to the mantle. So maybe with the lack of plate tectonics, it's just trapping heat in and not getting that convection going. Or maybe the core has solidified more. I mean, who knows? Venus is another one that will do a transit. It's inside the orbit of the Earth, so sometimes you'll get a transit of Venus in the same way as you can with transit of Mercury. But the next one isn't until 2117. So yeah, bit of a wait for that. Okay, I haven't got a specific slide for the Earth, but yeah, one thing to mention with the Earth in particular for this sequence is it's the first one with a moon. Mercury and Venus don't have natural satellites. The Earth does. It's the densest. It's the one with water. It's got the dynamic atmosphere. It's got the tectonics. So there's a lot of stuff going on. There actually, I should have said earlier on with these planets, you're looking at about 4.6 billion years ago that they were forming. So, in the previous video, when I was talking about the moon, the moon being that little bit younger, about 4.5 billion years. So, we're going back a long way here, and it's worth thinking in terms of the human life on Earth. You're probably looking at 300,000 years since anything sort of human-like was wandering around. So it's nothing really compared to 4.5 billion years. So anyway, that is Venus. Let's move on to planet 4 then with Mars. So Mars is a lot more interesting to look at. This is the red planet because it's covered essentially in rust. You've got iron oxide dust all over the place. And it's very high contrast to look at. It looks great through a telescope. It's still fairly bright. Okay, it's smaller than the Earth. Smaller than Venus, larger than Mercury. So it's the second smallest of the planets. But it's close enough and bright enough, and there's enough contrast on the surface of Mars that you can see a lot of stuff. I mean, you can see on here that we've got these polar ice caps, white top and bottom. We've got highlands, we've got lowlands. There are huge volcanoes on there. You've got plains and such like. With the volcanoes, you've got Olympus Mons. This is the really famous one. Particularly considering the size of the planet. Olympus Mons is 22 kilometers. It's that's Everest. Mount Everest is only 9 kilometers, so you're looking at 2.5 times the height of Mount Everest. And it's the base of it is nuts. It's like the size of, it's bigger than the island of Ireland. It's about 340 miles across. No, it's just mind-boggling how big it is. On a planet which is about half the radius of Earth. Now, continuing on from what we saw with Earth, Earth has got a moon, it's got a natural satellite. Mars has got two, Phobos and Deimos. Now, these aren't like they're not like the moon. These are small. The moon is big enough to have made itself round. It's got enough mass to gravitationally turn itself into a sphere. These two are small, they're irregular, they're just little things. They're like 22 kilometers and 12 kilometers in diameter. So they're tiny little things, but they are orbiting Mars. The origin of them isn't entirely certain. I mean, they may be captured asteroids, that's one possibility, or they might have been created at the same time that Mars was created. It's thought that Mars used to have a magnetic field, but it doesn't have one now. Doesn't have much of an atmosphere. It's got a bit of CO2 kicking around. Temperature is less extreme, minus 110 degrees C to maybe 35 degrees C. You can see why the thought of having humans go to Mars is more appealing than going to Venus or Mercury when you look at the temperature. The gravity is manageable on Mars as well, about a third of that of what you get on Earth. Plus, you've got the advantage of there's lots of water ice. The South Pole melted, they reckon, on Mars. If all of that water ice melted, it would cover the planet about 10 meters deep. I mean, the liquid water wouldn't last because the pressure's too low. There's not enough atmosphere. It helps to have an atmosphere just to keep the liquid there. It's fine when it's in ice form, but if it became liquid, it would just all disappear off. But there's a lot of things going for Mars. And looking at it through a small telescope, then you will see these features. Obviously, not in this detail, but you'll see the red color, you'll see the ice caps, you'll see the darker uplands. So it's a great one to look at through a telescope. Much of which can be said about the next planet, Jupiter, largest planet in the solar system. This is 11 times the diameter of Earth. So we've had a big jump up here in terms of size, but it's also a lot less dense. So, but 11 times the diameter of Earth, I mean, you're looking at maybe a tenth of the sun in terms of diameter. So now we've got a bigger jump in how long how long it takes to get round the sun as well. The orbit is so much bigger. You're looking at 12 Earth years for Jupiter to orbit the sun. It rotates very quickly though, and this is noticeable when you look at it through a telescope. It's about 10 hours to rotate all the way round. So if you're spending a 2 or 3 hour observing session looking at Jupiter, then you can see features like the red spot has moved significantly across your field of view, because 3 hours, that's about a third of a complete rotation. And that gives it, because it's made of gas, it gives us this bulge. You can see it's not spherical. It's definitely wider than it is high there. You get this equatorial bulge because of how quickly it's spinning around. And as I say, I mean, it's gas, some of it in liquid form. You haven't got this definite surface to it. It's about 3/4 hydrogen, 1/4 helium. You get cloud cover. So these coloured belts that you've got here, these clouds with all these, these are storms and wind patterns inside, all the detail that you're seeing in these belts, these coloured belts. So that's activity in the clouds, which there might be things like ammonia crystals. They got very high wind speed, sort of 200 miles an hour, and big storms like the Great Red Spot here. I mean, this is larger than Earth. It's smaller than it was in the past. I mean, it was much bigger 150 years ago, and it's shrinking, but you're going to get more of these storms forming. Now, it radiates more heat than it receives, and that is powered by it slowly contracting. So that gravitational energy is being radiated away. So it's shrinking and it's radiating. It's got, I mean, you'll notice it if you ever look at it through a telescope. It's got these 4 innermost moons, Io, Europa, Ganymede, Callisto. They're very noticeable. They move pretty quickly around. They're very easy to see. They're bright. You see them going across the face of Jupiter and dotting in behind and such like. 3 of them have got resonant orbits, Io, Europa, and Ganymede. So they get little pushes and pulls, these sort of resonances, as these 4 inner, what are known as the Galilean moons, because Galileo spotted them even through his primitive telescopes. They were that easy to see. And yeah, they're all pretty big, and you've got Jupiter itself, and they have little tugs on each other at certain points in orbits, and then they start orbiting in these resonant periods. So the orbit of Io is 4 times that of Ganymede, in terms of how quickly they're moving around. So the other thing as well with the moons, I mean, Io is an interesting one, that it gets flexed. Jupiter's got such a strong gravitational pull that when the moons get close in their close approach to Jupiter compared to their furthest away point, in these elliptical orbits that they're going around Jupiter in, at close approach and far approach, you're getting a difference in sort of gravitational flexing of these moons. And Io gets flexed quite a lot. And this is passing energy from Jupiter to these moons, because it is literally bending the surface and structure of these moons. And this leads to a lot of volcanic activity on Io because of the energy that's coming in from that flexing, gravitational flexing. So yeah, it's quite an interesting way. It's just so big, Jupiter. It's just got all of that mass and energy that it can throw around. So that is Jupiter. Next one is another big one, and probably the one that people recognize the most. Saturn is, I mean, this is even lower density. So we're still in these gas giants. It's still hydrogen, helium, mostly liquid, but it's less dense than water. So you've got this cold liquid hydrogen and helium. Probably got a rocky core, I think, is the current theory with Saturn. But then you've got all of that hydrogen and helium just sort of floating around it, and then gassy clouds and all of that, with this uncertain boundary between what is the planet, what is the atmosphere. Saturn is also very big. I mean, Jupiter is 11 times the radius of the Earth. Saturn, we're looking at 9 times the radius of the Earth. And it's got an enormous number of moons. I mean, Jupiter's got a lot. I know I mentioned 4 of them, the Galilean moons. Jupiter's got 100 or so. Saturn's got getting on for 150 of them. There's so many of them that a lot of them haven't even been named, really. They're fairly bland. They're not as exciting maybe as the Jupiter's moons. I mean, Titan is a big one. That's the one that's of most interest orbiting Saturn. It's the second largest moon in the solar system. It's got a denser atmosphere than Earth, and there's evidence of stable liquid. So yeah, Titan's quite an interesting character. But of the others, a lot of them are little. There's only 7 of the moons that have actually gravitationally rounded themselves, to become spheres. And the other sort of 140 odd, I mean, they're irregular little things. But there's a lot of them there nonetheless. Of course, the most notable feature of Saturn, because the surface of the planet isn't anywhere near as interesting as Jupiter, you can see it's got these bands, but they're not as interesting as the bands on Jupiter. But of course, who's looking at the bands? You've got the rings, and these are, I mean, the ring system in Saturn is far more involved and complex than the ring systems around any of the other outer planets, the non-terrestrial planets, because they all have rings to some extent, but nothing to match Saturn. They extend from about 4,000 miles out to 75,000 miles is what we're looking at. So about 7,000 to 120,000 kilometers. And it's still not entirely sure, there's no perfect theory for how these rings formed. Some people say they form with a planet. Some say that they're recent remains of, say, a moon or something that have been destroyed in the vicinity and then pulled apart by gravity. And we get really nice views of these rings because Saturn, the tilt of Saturn from the Earth changes quite considerably. So sometimes you look at it and you just see a boring view where you literally just see a line running through because the rings have closed, and you just see them side on. But then you get these great views. I mean, this is the rings opening up a bit, but you'll get some where if you've got, I don't know what that drawing was meant to be, you've got Saturn, they really open out and you can have these really wide rings and you can just see them in all their glory. Start seeing the gaps in between the rings. As for the content of the rings, you're looking at mostly water ice. 90% plus of it is water ice, but it then gets coated in stuff. It's a bit like we see with comets and other things. There's a lot of dust and carbon and things like this that are around other bits and bobs, and they stick to the ice. So that's what they have that outer coating, and that's the sort of reflectivity that we then get off of those rings. It's the most distant planet we can easily see with a naked eye. I mean, you can see Uranus with a push. Saturn is easy to pick out in the sky. It's fairly bright. It goes through cycles, sort of, I don't know, about 10 years, 12 years, thereabouts, as to which hemisphere of the Earth it's better to view it in. But it's easy to see. It's nowhere near as bright as Venus or Jupiter, but you can pick it out. Uranus, you have to know what you're looking at. And that's why it wasn't really picked out by the pre-telescope astronomers as being a planet. You'd really have to be on your game in order to spot how Uranus was moving. But Saturn, they could certainly pick out what was going on. So that brings us on nicely then to the 7th planet, then moving to Uranus. Not the most exciting one to look at. This hasn't really been visited that much because it's so far away. We're getting to 20 astronomical units now. This is the 3rd largest planet. It's the 4th most massive. It's about 4 times the diameter of the Earth, so it's a big step down from Jupiter and Saturn. But now we've got a change in composition. This is why they're referred to as ice giants. So with Jupiter and Saturn, I was saying that was hydrogen, helium. liquid form, then gas, and you've got various clouds going on. Now we're looking at having water, ammonia, methane. So you've got this in sort of ice form, you've got a rocky core, then you get liquid, you've got a hydrogen and helium atmosphere sort of envelope going around it. So we've got a change in structure, a change in composition compared to Jupiter and Saturn. Uranus is a bit weird that with the other planets, most of the other planets have either got very little axial tilt or they've got a bit of axial tilt. With Earth, Mars, they've got tilts of, sort of 23 degrees, 28 degrees, that sort of thing. And then you've got, what are the other ones? Neptune and Saturn have all got similar tilts. So you're looking at ones that don't tilt very much, like Mercury and Venus and Jupiter. And then you've got Earth, Mars, Saturn and Neptune, which tilt a bit, sort of in this 20 to 30 degrees sort of tilt. But then you've got Uranus, which is really odd. It's got this, it's like it's sideways. So it's tilted at about 82 degrees. So this is tilt from the plane of its orbit. So, we've got the Earth going around, there's the sun, there's the Earth. If that's the plane of the orbit, then Earth is tilted off at this angle of about 24 degrees. Now, with the axis of rotation of Uranus is almost in the plane of the orbit. So it's very odd. And it's probably the result of a collision with something else. Something hit it in the past and just knocked it off, misaligned the axis. As I mentioned when I was talking about Saturn, it was known of, but it wasn't known to be a planet for quite a while. So it was discovered as a planet in 1781. So this was William Herschel again. Yeah, he was looking around at all manner of stuff because he had a huge telescope. And he observed Uranus, noticed that it was a planet. This essentially doubled the size of the solar system, because before we were only getting out to 10 astronomical units with Saturn. We're now out to 20 with Uranus, so that's a big difference. Before people just assumed that it was, it was a star, right? They didn't realise it was going to be a planet. It's got some moons. It's got about 28 moons, something like that. They're the ones that people notice because they're named mostly after Shakespeare characters. It's also got a ring system, which is faint, but it is the second largest ring system after Saturn. But yeah, that's Uranus. Is not that exciting. It's got this sort of bluey green hue to it, but really you're just seeing some clouds. A bit of hydrogen helium sort of atmosphere envelope gives a bit of a bluey green glow. So not the most exciting. Which brings us on to the last of the 8. We finally make it to the end. Neptune. It's got a little bit more going on in the atmosphere. Not a lot. I mean, it's blue. This is a picture from Voyager. I want to say Voyager 2 was the one that went past. It was certainly one of the Voyagers. I think it was Voyager 2. Yeah, it's such a long way away. We're 30 astronomical units away. It takes a lot to get there. Not many satellites have been that far. This is a photo that it took. So this would have been in the late 80s. And it was a famous one because it's not that easy to make out. But right in the centre here, you've got what's known as the Great Dark Spot. So it's also got a storm similar to the Great Red Spot on Jupiter. But this has got crazily strong winds. So you're looking at 1,300 mile an hour winds, that sort of thing. And there have been other dark spots that have been observed. So it's got a similar sort of stormy atmosphere. But the structure is similar to Uranus. It's got a similar composition. It's this icy stuff with then a gassy envelope to it. So it does have a different structure and composition to Jupiter and Saturn. It wasn't known about until relatively recently. And it was actually found through analysis rather than observation. It was quite an interesting one. People started looking at the orbit of Uranus once people had discovered it was a planet. And there seemed to be these perturbations, like it was being pulled every now and again. The orbits weren't what the maths suggested for Uranus. And then people said, well, there must be something that's pulling on it. There must be another planet which is just tugging on the orbit of Uranus, and it'll have to be a planet of a certain size in a certain location. So they looked where people predicted, and lo and behold, they found Neptune in 1846. So yeah, that was quite the success for astronomers back in the 19th century. And yeah, it has this blue hue, so it fits with the Neptune and the sort of sea theme of it all. It's got 16 moons. Most of them aren't much to speak of. It's got one called Triton, which is spherical. It's the only one large enough to be spherical. And Triton orbits actually backwards compared to all of the other moons. You get most things move in the same direction in the solar system. We've got this angular momentum thing going on. So if you've got a conservation of momentum, and the original disk that was forming the solar system was all turning in one direction, you expect most things to be going the same way. You don't have some things orbiting one way and other things orbiting the other. By and large, everything goes the same way. Triton is an exception, one of the notable exceptions to that rule. And because it's orbiting in the opposite direction, I mean, it suggests that it was probably captured from from somewhere else. Maybe it came out the Kuiper Belt or something. Maybe it was something out there, a large asteroid, dwarf planet, something like that, and it's been captured by this big planet. Because of course, next stop after Neptune is the Kuiper Belt, where we've got all of these other objects. It's like a bigger, further away version of the asteroid belt. So maybe that's where Triton came from. Maybe some of the other moons of Neptune as well. I mean, who knows? So there you go. That's a quick whistle-stop tour of the 8 planets, just hitting the high spots and seeing what they all look like and what we should think about when we're describing them all.